So for today's lesson, we are going to be dealing with quite a bit of word problems. And of course, since we're dealing with vectors where we're dealing with direction and length, of course, bearings is going to come into play as well. So the direction of a vector can be given as a bearing. So bearings are frequently given in application problems because they show exact direction and angle. So a quadrant bearing is an acute angle between a vector and the north-south line or the y-axis. So we're always looking at that north and south direction. So a vector to the right over here is 60 degrees east of south. So it is written as south 60 degrees east. So you always lead with either north or south and then what direction that angle goes. Then your true bearing is a little bit different because your true bearing is measured clockwise from the north to the vector. So we're going to go, think about it like 12 o'clock. So if we're going clockwise, we're going to go from the north line all the way to the vector. And a true bearing is always given as 3 digits. So this vector is 120 degrees because we have 90 degrees in the actual quadrant and then 30 degrees left of the quadrant after the 60 on the other side. So since we do have 3 digits always, a true bearing of like 15 degrees is given as 0.15 degrees. So note that when a degree measure is given with no additional directions, it is assumed to be a true bearing. So for each of these vectors, we are going to give the quadrant bearing and the true bearing. So for number 1 here, we have 85 degrees in standard position. So our quadrant bearing, we're going to go from our north and we've headed towards the east because we're going to the right. So we only have 5 degrees left in the quadrant. So we are going to have north 5 degrees east. And then our true bearing is actually going to be 0.05 because we are already going clockwise from the north line. Then on number 2, we have 212 degrees in standard position, but coming from the south, we are heading west. And so if we go ahead and subtract 180 from 212, we are left with, 32 degrees right here. And so 32 degrees subtracted from the 90 is going to be 58 degrees. So we have 58 degrees right here. And so that's what we're going to use for our quadrant bearing. So we have south, 58 degrees west. And then our true bearing is going to go from that north line clockwise all the way over. And so that's going to be like 180 degrees plus the 58. So that's going to give us 238 degrees. Now number 3 here, we're given 24 degrees. And so we are headed towards from the north line over to the west. So this is going to be north 24 degrees west. And then our true bearing is going to be from that north line all the way around. And so we pretty much almost have 360 degrees minus 24. So that gives us 336 degrees. So let's look at some word problems. So we have an airplane is flying at a bearing of 245 degrees. So since that doesn't have anything on it, we are going to assume it's a true bearing. at 550 miles per hour. So we're going to give the velocity of the airplane as a vector in component form. So since we have our angle and we have essentially our magnitude, then we are going to put this in trigonometric form first. So V equals 550 cosine of, and we are going to need to go to standard position actually. So let's go ahead and look at that first. So 245 degrees is going to be over here. So we are going to need to get that angle in standard position. So we have, let's see, 180 degrees to here. So 245 minus 180, that is going to give us 65 degrees. So we have 65 degrees in this part of the quadrant, which leaves 25 left over here. So all the way around, so 180 plus 25 is going to be, wait, I'm adding, not subtracting, 205 degrees. Okay, so let's go back to writing the trigonometric form of that vector. So we have the V equals 550 times the cosine of 205, and then 550 times the sine of 205. So now I am going to go ahead and put these in my calculator. And I'm going to round to the nearest hundredth. So for cosine, we will have negative 498.47. And then for sine, we will have negative 232.44. All right, so for number 5, we have that a man pushes a lawnmower with a force of 25 pounds uphill at an angle of 40 degrees. So we're going to give the force exerted on the lawnmower as a vector in component form. So if we think about this on the graph, of course, he's pushing it uphill 40 degrees. So we have a 40-degree angle in quadrant 1. So that's in standard position, so we don't need to change it. So we'll have V equals, we have 25 pounds of force, so that's what we are going to use. And then we have the cosine of 40, and then 25 times the sine of 40. When we plug this into our calculator, we get V equals 19.15 and then 16.07. So now let's look at some resultant force applications. So if two or more forces are acting on an object, then the resultant force is the sum of the two vector forces. So we are going to be adding some vectors together. So on number 6, we have two tugboats that are pushing a barge. So if tugboat A is traveling at the direction of south 80 degrees east, so we're going to go ahead and draw a picture here. So tugboat A is heading southeast, so it's going this way. So 80 degrees. And tugboat B is traveling in a direction of north 65 degrees east. So 65 degrees this way. And both boats are pushing with a force of 400 pounds. So that's what I'm going to make my magnitude be. We need to find the magnitude and direction as a quadrant bearing of the resultant force. So here is the barge that they are pushing. So for tugboat A, So we're going to go ahead and call this vector A for tugboat A. That is going to be, see, 400. And then our angle, we had not thought about the angle yet. So we're going to kind of split this off. So we're going to look at that angle on its own. So if we're going southeast at 80 degrees, then we're going all the way around. So we have 270 plus 80. And so that gives you 350 degrees for standard position. And then for tugboat B, that 65 degrees is over here. So that leaves you with 25 down here for standard position. So tugboat B actually has a standard position of 25 degrees. So for vector A, we have 400 times the cosine of 350. And then we have 400 times the sine of 350. Then for tugboat B, that vector is going to be 400 times the cosine of 25, and then 400 times the sine of 25. So for our resultant force, to add these together, so vector A plus vector B, I would actually take 400 times the cosine of 350 and add 400 times the cosine of 25. And then for my sines, I'm going to do the same thing. 400 times the sine of 350 plus 400 times the sine of 25. And this is what I would actually put in my calculator. Once that is in my calculator, I get 756.45 and then 99.59. So I do need to find the magnitude and the direction. So for magnitude, we are going to have the square root of a squared, which is 756.45 squared, plus b squared, which is 99.59 squared. I'm just going to put that in my calculator, and that gives me 762.98 pounds of force. And then for that direction angle, we are going to have tangent of theta equals 99.59 over 756.45. That is going to give us theta as 7.5. And then we're going to turn that into a bearing, because remember, this is standard position. So going from north to the east, we're going to subtract 7.5 from 90, and that's going to give us north 82.5 degrees east. All right, so then for number 7, we have that 2 cranes are lifting a statue. Crane A is pulling with a force of 600 pounds at an angle of 35 degrees to the left of the statue. Crane B is pulling with a force of 750 pounds at an angle of 50 degrees to the right of the statue. So we need to find the magnitude and direction with respect to the horizontal of the resultant force. So of course we're going to draw a picture first. So we have our statue, we have the ground, and then crane A is pulling with a force of 600 pounds to the left of the statue. So we have 600 and then 35 degrees. And then we have crane B, that is 750 pounds. And it is 50 degrees to the right. So for our angles in standard position, 90 minus 50 is going to give you 40 for crane B. And then for crane A, you're going to have 90 plus 35, which is going to give you 125 degrees. So for crane A, that is going to be 600 times the cosine of 125, and then 600 times the sine of 125. For vector B, you're going to have 750 times the cosine of 40, and then 750 times the sine of 40. So I would put these in my calculator and add them together. So you're just going to add your A's together and your B's together. I'm not going to write that all out again. But VA plus VB is going to be equal to 230.39 and then 973.58. So our magnitude for V1 plus V2 is going to be the square root of 230.39 squared plus 973.58 squared. That gives us 1,000.47 pounds. And then for our direction angle, we have the tangent of theta equals 973.58 over 230.39. This means that theta is 76.69 degrees. And since it's respect to the horizontal, then we are going to keep it in standard position. Okay, so now let's look at some resultant velocity applications. So an airplane is traveling at a speed of 500 miles per hour at a bearing of 325 degrees. Once the airplane reaches a certain point, it encounters a wind velocity of 60 miles per hour in the direction of north 75 degrees west. Find the resultant speed and direction as a true bearing of the airplane. So what is happening here is that the airplane is going at a bearing of 325. So we know that that is a true bearing because it doesn't give us anything else. So since it's a true bearing, we're going to go from the north and go around. So we have 180 degrees, 270, and then here is our plane. So let's see, from that 325 minus the 270, because we went through 3 quadrants, we have 55 degrees here, which means over on this side, what's left of 90 is going to be 35 degrees. So 35 plus 90 gives us 125 degrees for the plane in standard position. So our vector for the plane, so we're going to call this vector P, is going to be 500 times the cosine of 125, and then 500 times the sine of 125. And then we are going to have a vector for the wind. So the wind is going 60 miles per hour in the direction of north 75 degrees west. So that would be this direction, 75 degrees. So we are going to add that to 90. So 90 plus 75 is 165 degrees. So we have 60 times the cosine of 165, and then 60 times the cosine, or not the cosine, the sine of 165. So we are going to add those together. So we have P plus W, and that is going to be negative 344.74, and then 425.11. So for our magnitude, we will have the square root, negative 344.74 squared, and then we have 425.11 squared. So that leaves us with 547.32 miles per hour. So then our direction angle, we have the tangent of theta equals negative 425.11 over 344.74. So that leaves us with theta, once we make adjustments for quadrant, at 320.96 degrees. All right, so then for problem 9, we have a baseball player runs forward at 15 feet per second and throws a baseball at a velocity of 80 feet per second at an angle of 20 degrees with the horizontal. What is the resultant speed and direction of the throw? So we have the baseball player running forward at 15 feet per second. So that actually doesn't have any angle on it. So vector 1 is just going to be that 15 feet per second on the horizontal. He's not going up, so that is going to be 0. So then the baseball is thrown at a velocity of 80 feet per second. So we add an angle of 20. So we are going to have 80 times the cosine of 20, and then 80 times the sine of 20. So for vector 1 plus vector 2, we are going to have 90.18 and 27.36. So that means that our magnitude is going to be 90.18 squared plus 27.36 squared, and that is 94.24 feet per second. And then our direction angle, we have the tangent of 27.36 over 90.18. So that leaves theta as 16.88 degrees. So for number 10, so we have a drone is flying at a speed of 40 miles per hour in the direction of south 70 degrees west. There is a wind of 15 miles per hour in the direction of south 10 degrees east. And we need to find the resultant magnitude and direction as a quadrant bearing of the drone. So if we draw a picture of this, then our drone is flying at a speed of 40 miles per hour, the direction of south 70 degrees west. So we have 70 degrees this way. And so going all the way around, we have 20 degrees left here, so 180 and 20 gives us 200 degrees for standard position. So for our drone vector, we have 40 miles per hour and then the cosine of 200 degrees. And then we have 40 miles per hour times the sine of 200 degrees. So then we have that wind speed at 15 miles per hour going in the direction of south 10 degrees east. So if we're going southeast 10 degrees, then that angle in standard position is going to be 280 degrees. So our wind speed is going to be 15 times the cosine of 280, and then 15 times the sine of 280. So our d plus w, when we put these in our calculator, is negative 34.98 and then negative 28.45. So our magnitude is the square root of negative 34.98 squared plus negative 28.45 squared. So that leaves us with 45.09 miles per hour. So then for our angle, we will have the tangent of theta equals 28.45 over 34.98, which makes theta 219.12 degrees. And then as a true bearing, because we do actually, well, not true bearing, a quadrant bearing, then that is going to be south 50.88 degrees west. All right, so our last couple of problems, we're dealing with horizontal and vertical components. So your vector can be resolved into a horizontal component and a vertical component. So the horizontal and vertical components are also called rectangular components. Because the rectangular components form a right triangle, you can use trigonometric ratios to find their magnitudes. So we're going to be using trig functions. So we have on 11, Danica is pulling a sled with a force of 400 newtons using a string. If the string makes a 35-degree angle with the ground, then find the magnitudes of the horizontal and the vertical components. So she's pulling the sled with 400 newtons. So we need to find the horizontal component, which we can call X, and the vertical, which we can call Y. So we will have for the horizontal component, we'll have the cosine of 35 degrees equals the absolute value of X over 400. And so the absolute value of X is 400 times cosine 35. And then X equals 327.66. Then for the vertical, we have the sine of 35 equals the absolute value of Y over 400. So the absolute value of Y equals 400 times the sine of 35. So Y is going to equal 229.43. So in this case, the horizontal force is 327.66 pounds, and the vertical is 229.43 pounds. So for our last problem, Ken is running 6 miles per hour in the direction of south 20 degrees west. So find the magnitudes of the horizontal and vertical components. So our horizontal will be X, our vertical will be Y. So we will have, for the horizontal, the cosine of 20 degrees equals the absolute value of X over 20. And then for the vertical, we will have the sine of 20 degrees equals the absolute value of Y over 20. So the absolute value of X will equal 20 times the cosine of 20. And that is 5.64. And then the sine of 20, that's the absolute value of Y, equals 20 times the sine of 20. So Y is going to equal 2.05. So then you have your horizontal force as 5.64 miles per hour. And then your vertical is 2.05 miles per hour.